Hello and welcome back to the lab. Today on the bench we have my Tektronix 7854. This scope has been waiting for a video for quite some time, and I just have not gotten around to getting this recorded with all the other stuff going in the lab, things like that. And to be frank, it's been kind of intimidating. The reason it's been kind of intimidating is this is the service manual for a 7904, the second fastest scope Tech made in the 7000 series. The 7104 was the 1 gigahertz version. 7904 is the 500 megahertz version. And this is the service manual, complete with troubleshooting and calibration procedures and everything that goes with it. This is the service manual for the 7854. So to say this is the most complex scope that Tech made in the 7000 series lineup would be absolutely accurate, and I don't know if anybody would disagree. So just from the length of the service documentation, it's an incredible undertaking to do an alignment and a calibration on one of these scopes, especially for standards. So to really do one of these mainframes, correctly, there's a bunch of standards that are needed. So we have a -01 and a -02 calibration plug-in for the 7000 series. One of the things that's a little strange with these is the -01 is the 500 megahertz, the -02 is the 1 gigahertz plug-in. This is far more rare than the -01. Theoretically, if you had to push it, you could do the calibration with two of these -01s. You just wouldn't have some of the higher end bandwidth of the -02. The calibration document does call for two of these. One of these is there's a checkerboard pattern that'll show up on the display, so we'll have to do the alignment to the display, because you actually have to calibrate this scope twice. So there's an analog section, there's a digital section. Both of those have a calibration and alignment procedure for them, and that's actually how we know this scope needs calibration and alignment, is because they're off, and I'll show that here in a second. But got to line up the digital, got to line up the analog. There's even a test card that goes along with this that I'm in the process of rebuilding. I'm going to attempt to do a calibration on this frame without it. The test card's function, it's used in one of the steps of the calibration process. It takes everything back to analog. All the digital stuff gets pulled out, and it does a thermal balancing between channel 1 and channel 2. It switches between them rapidly, and you can do a thermal balance adjustment. So incredibly detailed calibration and alignment procedure, which we're about to undertake. Some of the reasons for that is this is one of the first, if not the first, digital processing scope ever created. So this is capable of digitizing a waveform and storing it digitally and also measuring it digitally. We can see a bunch of waveform parameter measurements that this scope could do, and this was incredibly high technology for the day. So high, in fact, that it was only introduced in 1980, which was quite down the line of the 7000 series to get started. It also didn't migrate to the faster scopes due to 400 megahertz being about as fast as it could run, or at least as this frame runs. So we didn't see any of the 500 or 1000 megahertz scopes with the digital processing. Now, on the flip side of that coin, I would imagine due to cost, it never went into the slower scopes. So we never saw this in the 200 megahertz series, the 100 megahertz series. One example of a 100 megahertz version being the 7603 right over here. This was also a horrifically expensive scope for the time, with a 1981 catalog price of $10,500. The 2023 equivalent of that being $35,500. So this scope frame essentially costs about as much as a car back then and now. So for $35,500, I can buy a reasonably priced sedan or something equivalent to that today. with the addition of the waveform calculator keyboard, which is a cable that plugs into the back of the scope, a technician is able to do math on the entire waveform itself. I can add two waveforms together, subtract two waveforms, things like that. It can do some pretty wild math and is also programmable for certain situations. Waveforms can be generated somewhat programmatically, which some of the alignment waveforms are. They'll draw a square and to help line up the digital section. So we'll get it fired up, and I'll show you guys the problem that needs to be corrected to get this thing back to rights. All right, we'll give it some power. This scope's been used a few times, kicked on, turned on, done things, so we know it works. In a previous video, we changed out all the lamps to LEDs. They're still running very well, and we also have self-test complete. Okay, so setting the camera up for a little bit of shutter speed changes so we actually get some decent scanning on the display. Everything looks good. I'm going to fire up the... Well, we'll just do this all on camera. So we'll go to... turn it to a scope. And we'll give it some signal. AC coupling is fine. A time base. We'll have to give it some intensity. So we'll do an acquisition. The scope's taking a little bit. It's sampling a waveform. When the busy light goes out, everything is done. So everything was good there. Now, what we're going to do is we'll flip over to the stored waveform. And so we can see our stored lit up, and the waveform is there. This is still a reasonable facsimile of the waveform. Everything looks good, but if I overlay both, we can see they are off and do not line up. We'll zoom in on that. So essentially, these waveforms should be as close as they possibly can to overlapping each other. It's off a little bit, but it's off enough where the measurements that this system can take would actually kind of somewhat be of a problem. So that's actually a quick test to see if your scope needs alignment. Set up a decent waveform, get it up, sample it, overlay, real-time, and sampled, because if I turn off the function generator, we can see it goes away. So it is a real-time analog and digital waveform. But this proves, beyond a shadow of a doubt, that this frame needs alignment, and it's the digital and the analog amplifiers are not lined up on top of each other, and that needs to be adjusted. Unregulated voltage has gotten through at the bottom of the power supply. Ground is just hooked to the chassis, and we're looking for a 108 or 107.5 to 108.5. We're at 108.0, so right in the middle, and our pre-reg is good. Next stop is I got to put the bottom cover back on, and then we actually have to pull the power supply out to expose the pins to take some measurements on the DC rails. Okay, we have our meter up here, and we're at negative 50 volt. We're checking on the negative 50 volt rail. Negative 50 volts is good. And we'll check positive 50 volts. Not going to complain about that. Negative 15 volts. I'm good to 14.85, so that's perfectly healthy, plus 5 volts. I am good to 0.49, so that's good, plus 15 volts. Good to 14.85 and plus 50 volts. And that looks great. So power supply is good and healthy. Okay, we got to check the 100-volt test point on the high voltage board. It goes without saying, this is the high voltage board. You do have to take the high voltage cover off. This does run at elevated voltages. It's in the name, the high voltage board. Take care. If you're following along, you are doing so at your own risk to you and your equipment. Gonna see if we can't clean that up a little bit, find another 9 volts. It should also be noted that on this board there is several kV because the anode voltage comes out of this board, so use extreme care. We do need to adjust 115. We're looking for 100 volts, and we are light on the high voltage, so let's see what happens when we tweak a pot. And just bumping the pot brought it to 100 volts. So that is what we're looking for right there, 100 even. Safety covers are back in place, and we are on to step B3, Z-axis voltage levels. Well, the step pulse could be a bit better on the Z-axis, so we're going to tweak a little bit of adjustment on that. The Z-axis board on this scope is hanging out the back of the case here. And the adjustments, have to move the camera again. The adjustments are this group of adjustments down here, these R's and C's. And those need to be adjusted with a low capacitance screwdriver. So what we're going to do is see if we can't make this pulse shape a little bit better. Okay, we have a square edge that's looking better. However, our rise time is a bit light. It's supposed to be, well, 10 to 15 nanoseconds, so we're down at 11 nanoseconds, so it's slowed up a little bit, but within 15, that's not bad. 11's good. That's actually right in the middle of the rise time, and we have a nicer square corner for the Z-axis composition. Now, this is brightness. Any aberrations or anything in this waveform would be fluctuations of intensity on display and a couple of other things. So that is what we are adjusting at this point. Test point 122 is up here towards the top of the board to chassis ground, and this one's actually done with a voltmeter. Moving up to the voltmeter, we're at 1.78, and all we are supposed to do is take a note of that. Now we move to test point 103, which is where? Right below it. Test point 103. And we need to be within 40 millivolts less of the previous reading within 10 millivolts. So that's oddly stated, but our previous reading was 1.78420. We're going to subtract minus 1.76498. And we're actually off by 10 millivolts because that gives us a total of 019. There's confusion here because the manual is missing a step. You're supposed to set the time bases to 1 milliseconds per division, auto AC and external, for a free running trace. That is clear and an easy part. It then says obtain a free running display. Then it says remove time base from the A horizontal component. It never says select the A horizontal component that you have removed. So when doing this adjustment, the spot where the time base is missing needs to be selected. So we'll do this again. So test point 122 is 1.80. Test point 2 is 1765, which I believe is actually going to be in spec and we don't need to adjust anything. We are 36 millivolts down. We are within 10 millivolts. We do not need to mess with this adjustment. Okay, TP83 is on the far right of the board when looking at it from the back. And The voltmeter needs to be set for a precision voltage of 200 volts, 200 volt range. Our targets are 120 to 126. DMM says 123.3. That's dead in the middle. Yeah, 123. That does not need to be adjusted at all. Contrast is a front panel control, so we're going to leave that set as is for right now. And I'm going to put the cover back on the Z-axis board because we are done with the Z-axis board at the moment, and we're going to get into geometry and alignment, but I need to rotate the scope 90 degrees so we can actually see the front panel, and I don't want all the high voltage stuff hanging off the back of the board. So we'll get that buttoned up, and now it's going to get into the important alignments and calibrations due to the fact that we had display problems, and we are about to tackle display geometry and alignment and all that good stuff. So this is really where we should need to make some adjustments. Okay, after setting up the signal standardizers, which we'll take a look at here in a second, I had to crack the case open and high voltage case back open and hook up TP 156. And with the power on, we should be reading 34 to 36 volts with focus control about mid-range. 34.5, so that's going to work quite well. Okay, we're supposed to grade the display by eye, and this is looking very good, although I'm seeing it shifting and we're seeing some bowing out here, so my geometry is off as well as my expansion on the display is off. So this is probably partially what's causing our inconsistencies with the digitizing section. You're seeing oscillators, the pulsing in the screen, and I apologize for that for anybody who's sensitive, is free-running oscillators are syncing up and desyncing as they go through, as they warm up. Both of the signal standardizers are set to 1 kilohertz or 100 kilohertz. They're not exactly 100 kilohertz. That's why the display stopped and then started rolling back the other way. That's two free-running oscillators colliding with each other as opposed to a fault with the scope. So that's actually kind of normal as this warms up, which is actually the next thing we're going to tackle. So I need to expose the Y alignment, which is over here, the geometry alignment's back here, and between the two of them, I need to make these as square as possible. Okay, it's not perfect, but it's not bad. But I also have a lot of adjustments that we have to do in a different area of the scope. So what's going on here, and what can I see, what's bothering me, and what do we need to fix? Down here, I don't know if the camera's picking it up, but there's some distortion in the CRT down here. I also have some sweep linearity problems where the sweep is good and then it starts deviating as these lines should be lined up. And so I have sweep linearity problems. Now, sweep linearity is actually two places where that's adjusted. One, it's adjusted in the time bases themselves, and it's also adjusted in the frame. So I checked. I've calibrated this time base personally here in the lab. I have not calibrated this time base, and I have not calibrated this 7B87 that we were using before. And why is this so important? Well, let's switch out to the 7B87. Alt and chop. So we can also see the linearity is a little different with the 7B87. Part of that is because the sweep linearity is done two ways. There's a horizontal and vertical amplifier in the frame, and there's also drive signals that drive those amplifiers in the plugins. So the plugins could be right, the frame could be wrong. The frame could be wrong, the plugins could be right. Kind of chicken and an egg problem. That's where these signal standardizers come in, is when you do the horizontal vertical gain and you set up this grid pattern, these are truth. So everything ties back to a plug-in. You do the frame, then you do the horizontals, then you do the verticals. Everything ties back into the step gain of one of these signal calibrators, or both in this case. This isn't looking too bad, and we will be able to address the display issues with this scope. But for right now, this is the best we can get because I still have to do vertical and horizontal amplifiers and a couple of other things. So what we're looking for in this one is X and Y alignment. So X will be trace rotation. Y will be Y rotation, which is up here. And geometry is expansion and compression. If you can imagine taking the center point and pulling it and pushing it into the frame and it distorting the grid pattern in that kind of way, that's kind of what geometry is doing. Is geometry is taking the center point and pulling it closer or pushing it further away and distorting the grid pattern in that way. So to get the best results, we have to get all of those balanced so this grid lines up as best it can. I think that's going to be as lined up as the world's going to let me get it. So essentially, how was I lining this up? I was looking for 90s at the corners and then equal thickness on the intensified lines across as much of the graticule as I could get. So with positioning the vertical and the horizontal, so I can move it up and down, I was looking for equal thickness of the lines on the centers and then square corners. That's what allowed me to set the geometry and the X and Y alignment. So this is pretty good. This is not good for measurement. We have linearity problems. There's a couple of other things. So the horizontal and vertical amplifiers do need to be adjusted. We also know the digital amplifier does need to be adjusted in this scope. So calibration process was needed. But for this part, for this step in the process, this is actually looking really, really good. All right, my grid bias is running a little bit low. This should extinguish the spot at 21.7 volts. So what we need to do is bump this up so we see it. There we go. Oh, that's coming up. So grid bias should just turn that spot off right there at 21 volts. It wasn't turning on until 29, so that should give us some more intensity on the tube, actually. Yeah. That right there is 22.5 for grid bias. So yeah, our grid bias was running a little light. That is a dirty, that flashing is a dirty potentiometer. I have to fix that. All right, in an effort to keep some of these videos on the shorter side and not as dense as the calibration on this thing can be, I think we're going to break this up into a couple of parts. The next two sections in the calibration manual, probably going to breeze through really, really rapidly. If you guys would like to see a detailed version of those, let me know in the comments below. The next two sections are the calibrator camera function, essentially for the scope camera that goes in the front, as well as the trigger system. Now, the trigger system in this frame is working absolutely flawlessly. It has no problems on it, and that is one of the more fiddly systems to adjust on one of these 7000 series. So sometimes if it's working, it can be best to just let it lie. If it's having problems, absolutely it needs adjustment, and sometimes we have to get into the weeds. But on this particular frame, the trigger system's fine, the calibrator's fine, and they don't even make the film for the scope cameras anymore, so they're not even useful. So probably going to skip the calibrator section and the trigger section. The calibrator can be very rapidly checked with a modern scope. Do the waveforms look right? Are the voltages right? Is the edges good? Now, it does have a pretty fast edge coming out of the calibrator. So some of the slower scopes may struggle reading it directly. I've got some gigahertz stuff here in the lab. We can just pump it in and take a look at the fast edge, see if it needs to be adjusted. Frequency-wise, frequency counter these days makes short work of it. So there are three critical systems after that we'll cover in additional videos. The horizontal and vertical, probably do those as one video. And we will also do the GA display system, which is essentially the digital side of this scope. So realistically, we're not even a quarter of the way there yet, and we've already put a substantial amount of time into this frame. But we'll keep going, and it's going very, very well. I'm not unhappy with the way this is aligning up at this point, but we'll have to dig into it a little bit further to finish up the process. So With that, as always, thank you to everybody who supports the channel via Patreon. If you would like to support the channel and or check out some additional content, check out the Patreon page. They're running ahead from video releases. Do all the YouTube things. Hit subscribe, like, comment. As always, I will see everybody in the next video. More is always on the way.